Good afternoon, everyone. This is my 25th lecture. Welcome to my lecture series. Before I start my lecture, let me introduce myself. I am Rinki Bhaumik, Assistant Professor, Department of Physics, JIS College of Engineering. Your paper name, as you know, Physics 2. The paper code is PH301. This is for CSE and IT second year students. These lectures, total 36 lectures will be there. This is a 3 credit lecture and total 3 lectures per week will be there. In 25th lecture, we are going to discuss about quantum mechanics. This is simply a this will be the continuation of previous lecture. In my previous lecture, I already discussed about normalization process, what is orthogonality and so on. Now today we are going to discuss, we are not actually going to discuss, but we are going to do the theory and also mainly the problem and numericals with respect to those theory. Today we'll again recapitulate the what is eigenfunction, eigenvalue, and with respect to that we'll do some numerical also. Now we'll do a numerical on what is normalization. With respect to the normalization, we'll do a numerical also. So these are the topics on which we'll do discussion today. But before I start my discussion, let's have a look on a video.
One of the most amazing facts in physics is this. Everything in the universe, from light to electrons to atoms, behaves like both a particle and a wave at the same time. All of the other weird stuff you might have heard about quantum physics, Schrodinger's cat, God playing dice, spooky action at a distance, all of it follows directly from the fact that everything has both particle and wave nature. This might sound crazy. If you look around, you'll see waves in water and particles of rock, and they're nothing alike. So why would you think to combine them? Physicists didn't just decide to mash these things together out of nowhere. Rather, they were led to the dual nature of the universe through a process of small steps, fitting together lots of bits of evidence, like pieces in a puzzle. The first person to seriously suggest the dual nature of light was Albert Einstein in 1905. But he was picking up an earlier idea from Max Planck. Planck explained the colors of light emitted by hot objects, like the filament in a light bulb. But to do it, he needed a desperate trick. He said the object was made up of oscillators that could only emit light in discrete chunks, units of energy that depend on the frequency of the light. Planck was never really happy with this, but Einstein picked it up and ran with it. He applied Planck's idea to light itself, saying that light, which everybody knew was a wave, is really a stream of photons, each with a discrete amount of energy. Einstein himself called this the only truly revolutionary thing he did, but it explains the way light shining on a metal surface knocks loose electrons. Even people who hated the idea had to agree that it works brilliantly. The next puzzle piece came from Ernest Rutherford in England. In 1909, Ernest Marsden and Hans Geiger, working for Rutherford, shot alpha particles at gold atoms and were stunned to find that some bounced straight backwards. This showed that most of the mass of the atom is concentrated in a tiny nucleus. The cartoon atom you learn in grade school, with electrons orbiting like a miniature solar system, that's Rutherford's. There's one little problem with Rutherford's atom. It can't work. Classical physics tells us that an electron whipping around in a circle emits light, and we use this all the time to generate radio waves and X-rays. Rutherford's atom should spray X-rays in all directions for a brief instant before the electron spirals in to crash into the nucleus. But Niels Bohr, a Danish theoretical physicist working with Rutherford, pointed out that atoms obviously exist, so maybe the rules of physics needed to change. Bohr proposed that an electron in certain special orbits doesn't emit any light at all, Atoms absorb and emit light only when electrons change orbits, and the frequency of the light depends on the energy difference in just the way Planck and Einstein introduced. Bohr's atom fixes Rutherford's problem and explains why atoms emit only very specific colors of light. Each element has its own special orbits, and thus its own unique set of frequencies. The Bohr model has one tiny problem. There's no reason for those orbits to be special. But Louis de Broglie, a French PhD student, brought everything full circle. He pointed out that if light, which everyone knew is a wave, behaves like a particle, maybe the electron, which everyone knew is a particle, behaves like a wave. And if electrons are waves, it's easy to explain Bohr's rule for picking out the special orbits. Once you have the idea that electrons behave like waves, you can go look for it. And within a few years, scientists in the US and UK had observed wave behavior from electrons. These days, we have a wonderfully clear demonstration of this, shooting single electrons at a barrier with slits cut in it. Each electron is detected at a specific place at a specific time, like a particle. But when you repeat the experiment many times, all the individual electrons trace out a pattern of stripes, characteristic of wave behavior. The idea that particles behave like waves and vice versa is one of the strangest and most powerful in physics. Richard Feynman famously said that this illustrates the central mystery of quantum mechanics. Everything else follows from this, like pieces of a puzzle falling into place.
Good afternoon everyone. Today we are going to solve some problems of quantum mechanics. So in the last class we already discussed about some theory on quantum mechanics like normalization process, what is eigenfunction, what is eigenvalue, and what is wave function. About all these topics we discussed. So today we are going to do some numerical with respect to those theories. So the first problem is, all of you note down the problem. Consider a function y equal to a e to the power alpha x. This is the wave function where a and alpha are real positive wave function. These are the positive quantities. The question is, can it represent the wave nature of a particle? This is the question. Okay. So when the question is, can it represent the wave nature of the particle? For that case, we have to first find out psi square. Okay. Psi square. Now before that, psi equal to a e to the power alpha x, that is the wave function. So therefore psi square will be obviously a square e to the power 2 alpha into x. Now, if we do this integration minus infinity to plus infinity, mod of psi square dx equal to, then it will be minus infinity to plus infinity a square e to the power 2 alpha x dx. It will be equal to a square by 2 alpha e to the power 2 alpha x. So if we put the values, then minus infinity to plus infinity. Okay, will be equal to obviously infinity. The wave function psi is not a normalizable wave function. Because here we are getting psi square equal to infinity. If we get psi square equal to 1, then we can say that okay, this is a normalizable wave function. But since mod of psi square minus infinity to plus infinity dx is equal to infinity we have got, so that is why psi is not a normalizable wave function. The square of its modulus becomes infinite as x tends to infinity. So psi cannot be a acceptable wave function. To be the acceptable wave function here, the psi square, see this is the normalization condition as I previously said. Psi is a normalization condition. Minus infinity to plus infinity mod of psi square dx. If it is equal to 1, then it is always a normalizable wave function, and if it is a normalizable wave function, then we can say that it represents the wave nature of the particle. Okay, so since it does not have the nature, so that's why it will be not be the, it cannot represent the wave nature of a particle. So this is first numerical. So whenever we will be asked to find out the can it represent the wave nature of the particle or not, then we have to find out the normalization condition. Now second condition, second numerical. The second numerical is which of the following functions are of, it will be eigenfunction, which of the following functions are eigenfunctions of operator. D square dx square the first one is a sin kx. Now let's do the first one, a sin kx. So a sin kx, if d square dx square, if we do a sin kx, then what you are getting first? K square a sin kx, but there will be a minus sign. So finally we are getting minus k square sin. In my last class I already said that after any operation, means here the operation is d square dx square and the wave function is a sin kx. So after doing this operation, if we get back the same wave function, which is here a sin kx, means psi, if we get back psi, then it will be the eigenfunction of the operator with some eigenvalue. Here it is minus k square. Here the eigenvalue is minus k square. This is the eigenvalue. Now next one is b to the power kx. So d square dx square d to the power kx. If we do it, then finally what we are getting? K square b e to the power kx. That means the k square psi, isn't it? So that means k square psi. After the operation here, again we are getting the psi wave function with some eigenvalue, that is your k square. Very simple. Now if we do another one, next one, that is your d square dx square a ln x. So if we do this integration d dx of a 1 by x, next a minus 1 by x square. So after this operation, we can see clearly here that we are not getting back the wave function same, because here the wave function is a sin ln x, and here after the operation we are getting minus of 1 by x square. That means this is not same as the initial wave function. So therefore this cannot be the eigenfunction of the operator, because we are not getting back the same wave function. Now the next problem is about commutation relation. So what is the commutation relation? We discussed in the last class. Now today we are going to do some problem with respect to the commutation relation. Okay. So the problem is, first a cap equal to suppose sin x. Okay. Now b cap equal to d dx. A cap equal to sin x and b cap equal to d dx. So how actually it commutes, means a hat and b hat commute to each other or not, that we have to prove today. So let's first recapitulate what was the commutation relation. If you go there, then you can remember a cap b cap. If it is equal to 0, then they do commute to each other. Now a cap b cap equal to actually a cap b cap minus b cap a cap is equal to 0. So now here there will be a wave function psi. Here there will be a wave function psi. So first, if we put sin x comma d dx এর whole psi is equal to sin x d psi by dx minus d dx sin x psi. Isn't it? So if you do it, then what we are getting? Sin x d psi by dx minus sin x again d psi by dx is equal to, there will be another term, only sin x ddx of sin x, and there will be also a psi. So finally what we are getting? Minus psi cos x, minus psi cos x. That means Finally, a cap comma b cap psi is equal to minus psi cos x. So if we compare both sides, then what we are getting, a cap comma b cap is equal to minus cos x. Therefore, a cap b cap minus b cap a cap equal to minus cos x. That means what we know that the condition of the commutation is a cap b cap must be equal to 0, but here we are getting a cap b cap minus b cap a cap, that is in third bracket a cap b cap, that is equal to minus cos x. So that means the commutation relation does not satisfy here. So the answer will be, the question was whether the a cap b cap commute to each other or not. So by the answer we can say that they do not commute to each other. Okay, so we have to write finally that a cap and b cap do not commute to each other. Commute to each other. So this is the answer. Now our next problem will also be about the commutation relation. Here a cap comma b cap is equal to minus b cap comma a cap. This one we have to prove. This is fourth problem. It's very simple. First, a cap comma b cap psi is equal to, the formula is as we know already, a cap b cap minus b cap a cap psi is equal to a cap b cap psi minus b cap a cap psi is equal to, suppose this is your equation number 1. Okay, now on the RHS or on the right hand side, if you take b cap a cap psi is equal to minus of a cap b cap minus b cap a cap psi. This is suppose your equation. Now comparing both sides, we can write easily that a cap comma b cap is equal to minus b cap comma a cap. So this one is very easy. You just have to know the formula of a cap comma b cap in third bracket. So therefore a cap b cap minus b cap a cap. Now again b cap a cap equal to minus of a cap b cap minus b cap a cap, because as we know that b cap a cap, if we expand it, then what we are getting, that b cap a cap minus a cap b cap. So if you take a common minus, then finally we can get it from here, b cap a cap minus a cap b cap. So thus we can prove that a cap b cap equal to minus of b cap a cap. Now to today's last problem, this is totally a different problem, kind of. This is fifth one for today. Find the eigenfunction. Most of the time the eigenfunction is given, we have to find eigenvalue. But here today we have to find eigenfunction of the momentum operator. As we know, the expression of momentum operator is E exact equals to minus I h cut ddx, corresponding to eigenvalue p. Okay, so how to do it? First, as per the problem, p x cap psi will be equal to p psi, because p exact is the here operator and p is the eigenvalue. So as per the problem, here I have written here p x cap psi equal to p psi. Now minus I h cut ddx of psi is equal to p psi. So minus I h cut d psi by psi equal to p into dx. Now integrating both sides. Integrating both sides. What we are getting, minus I h cut ln psi is equal to px plus c. Therefore, ln psi is equal to minus px by I h cut minus c by I h cut. So psi is equal to d exponential Ipx by h cut. So this is the answer. That means here we first have put the formula of the eigenfunction and eigenvalue, that is px psi is equal to p psi. Now px equals to minus I h cut ddx psi is equal to p psi. Here then we have done the integration, and if we do the integration thoroughly, then finally we have got psi equal to d exponential I px by h cut. Now interestingly, if we initially if we do consider this eigenfunction, then if we again put this eigenfunction on the operator, that is your minus I cut ddx, then we can get the eigenvalue p like this. Okay, so if any time, most of the time eigenfunction has been given, if any time we have to face this kind of problem where operator is given and eigenvalue is given, but the eigenfunction we have to find, then we have to use this method, and then we have to find the eigenfunction. So these are some basic problems with respect to the theories which we discussed in our last class. Hope all the numericals and problems which we did today, that is clear to you. we must have to do the practice. If we don't do the practice, then obviously it will not be easy to do, but you must do the practice, that's why, so that you can attend. Okay, so and if you have any question, please feel free to ask. So thank you today.